Hello, and welcome to Analam Electronics Series 1100 training tape. My name's Harley Smith, and in this program I'll take you step by step through the fundamentals of CNC programming and startup at the machine. But first, let's review the basics of dimensioning theory. A mill has three axes of motion, X, Y, and Z. The X-axis runs back and forth, corresponding to the length of the part. The Y-axis runs in and out, corresponding to the width of the part, and the Z-axis runs up and down, corresponding to the depth of the part. All dimensions are either positive or negative numbers. Any X-axis dimension to the right of 0 is a positive number. X-axis dimensions to the left of 0 are negative numbers. Any Y-axis dimensions away from 0 are positive numbers, and any Y-axis dimensions in front of 0 are negative numbers. Any Z-axis dimensions above the workpiece 0 are positive numbers, while Z-axis dimension into the workpiece are negative numbers. The point where all three axes intersect is our 0 reference point. This system of measurement is known as the Cartesian coordinate system, and it can be used to describe any point. For example, here is a center reference blueprint with 4 hole locations. Each hole location can be described as a specific XY position taken from 0. Hole number 1 is at X positive 3, Y positive 2. Hole number 2 is at X negative 2, Y positive 3. Hole number 3 is at X negative 3, Y negative 2. And hole number 4 is at X positive 2, Y negative 3. These are called absolute dimensions because all are taken from an absolute 0 location. Another way to describe these locations is the distance they are from one another, or as incremental dimensions. Let's say the tool is at hole number 1 and we want to go to hole number 2. The distance would be X negative 5, Y positive 1, incremental. The distance from hole 2 to hole 3 would be X negative 1, Y negative 5, incremental. And the distance from hole number 3 to hole number 4 would be X positive 5, Y negative 1, incremental. The distance from hole number 4 back to hole number 1 would be X positive 1, Y positive 5. That's all there is to it. If you've done CNC programming before, you should breeze right through this section. But if this material is new to you, make sure you understand everything in this section before moving on. Stop the tape here, review your manual, and do all of the exercises in your workbook. When we return, we'll do an overview of the Series 1100 console. Looking at the console, the faceplate is laid out this way. We have a 14-inch monochrome CRT here, and the keyboard is laid out into 4 sections. At the bottom of the control, we have the soft keys. The soft keys are used most often in programming. They're used to select different functions. The box on the screen lines up above each soft key, and that's how you select each one. Anything that is active at the time will be highlighted, such as the manual mode here. The top section contains the X, Y, Z keys and the numeric keys here. We also have an absolute incremental key and a plus-minus key. The center section has a clear key, an enter key, and a cursor movement, left, right, up, and down. The section below it is used for jogging the machine in the manual mode. The hand key will select rapid, feed, jog 100, 10, and 1. When you select the type of movement, you simply select the X plus or X minus key, Y plus or Y minus key, and in the case of a 3-axis, Z plus or Z minus. You also have a servo reset key for powering up the servo motors, and spindle keys if those functions are available on the machine. You also have a feed rate override knob, an emergency stop key, and cycle start and cycle stop keys. The CRT screen is laid out so that you have the same screen whether you're in manual, single step, or auto mode. Here in the upper left corner is your axis position display. It tells you where the table is sitting in reference to absolute 0. You also have 2 status areas. The small status area tells you what block number you're on, what the current tool number is, at what feed rate you're running, the tool diameter, and the percentage of maximum feed from the feed rate override switch. The upper right status area has quite a bit of information. It tells you which mode you're in, whether you're in absolute or incremental, inch or millimeter, whether you're halted or running, cutting an arc, a line, or a rapid move. It also tells you what your current program name is. And if you are executing a loop, it will count down. Dwells will count down. There is an RPM display if it's installed on the machine. It also tells you whether you're in rapid, feed, jog 100, 10, or 1. And it tells you whether your coolant is on or off. The dark section below it will display the CNC program when you're in the single step or auto mode. To demonstrate, I'll power up the servos, go into single step mode, and you'll see the program appear here. As the program is executing, the blocks will scroll up the screen. Just below that section is the message line. Especially in 2-axis, you will get messages to position the Z-axis and press start, or prepare for a tool change and press start. There are a few points of interest in the edit mode. Looking at the soft keys, we have a teach-in mode which allows us to input manual positions into the program. We have a draw mode which will allow us to display our program. We have a drill window which will let us select basic drill, drill off, pattern, and bolt hole. We have a pocket menu which allows us to program rectangular pockets, circular pockets, frame milling, hole milling, and irregular pocket milling cycles. We have a mill menu which allows us to select rapid, line, arc, Z-move, set feed rate, set 0, do a home function, do an ellipse or a spiral. The previous key will bring us back to the previous menu. We can call up a tool number or cancel a tool with soft key F6. Our calculator keys are available here. Subprogram brings up the subprogram mode where we can define a sub, call a sub, end a program or a subprogram, set up a loop to loop a subprogram, do rotation, mirror, or scaling, set up a time dwell or dwell forever, and select an M code if M codes are installed on the machine. The miscellaneous soft key allows us to search a block number. For example, search block 17. We can page up 1 page at a time, which consists of about 9 lines, or page down 1 page at a time. We can quickly go to the beginning of the program or to the end of the program, which is especially handy in long programs. And we have a function called quit. If you're in an editing session and you make a mistake and you just want to start over again without saving the program, you can select quit. It will exit back out under the original program name without saving those changes. That completes our overview. Stop the tape here and review the console on your own. When we return, we'll apply what we've learned with a sample part program.
Hello, my name is Dave McCarthy, CNC Product Manager for Analam Electronics Incorporated. I'm going to take you through the programming process for a 3-axis Series 1100 control on a workpiece that contains a contour around the outside, a circular pocket near the center of the part, and a bolt hole circle around that circular pocket. In the 7 basic steps of machining a part on a CNC control, there has to be certain things decided before we even start programming, and certainly things done before we start cutting. Number 1, you decide how you're going to hold the workpiece, whether it be in a vise or a fixture. Step number 2 is to decide which tools you're going to use and what order you're going to use them in to machine the part. Step 3 is to actually program the workpiece. And step 4 would be to draw the workpiece using draw graphics on the control to find any mistakes that you may have made. Then we get into the setup of the workpiece, starting with step 5, defining X0, Y0, or setting absolute 0 on the workpiece with an edge finder or an indicator. The 6th step is to do the tool length offsets, and that's to describe to the control the distance from the bottom of the tool to the top of the workpiece for each separate tool. And then finally to machine the workpiece. The first thing I want to do is to drill the part, then we'll come in and mill the part afterwards. So the first step we want to take is to ensure we're in the manual mode, then go to press soft key F2 program. This is where we create and delete programs and edit programs. I'll press F2, create a new program, and I'll give it a name. And I can use the ASCII table here to find the full alphabet, or I could just use the X, Y, Z keys and the numeric keys, either one. I'll name this program EX-2. So I search the E and enter it, search out the X, enter, and I can use the -2 from this area of the keyboard. Turn off the ASCII table, enter the program. The program is created and shown here on the screen. The next step, we go into edit mode. With a brand new program, the screen will remain mostly blank, except for the soft keys here on the bottom of the screen and some status up here near the top of the screen. The first step always in any new program will be to set your dimensions to absolute. We do that with this key here, the absolute incremental key. And it can be toggled back and forth. We want to leave it at absolute and press F10 to save. F10 is always the save key, and we'll use that to enter each block into the program. Okay. Thinking about how we want to machine this, we wanted to drill it first. So I want to set up, first of all, a drill cycle. In a 3-axis control, we have to tell the control how to drill, whether to do a basic drill cycle, a peck drill cycle, or a boring cycle. I'm going to select the drill key, which is F3, and select a peck drilling cycle. When I select it, the graphics and entry come up here on the screen, and I fill in the blanks. Any blanks, any entries that are initially filled with 0 are required to be filled in. The entries that are blank are optional entries. We'll start off with a Z depth, minus 0.3. Starting height, 0.100 above the workpiece. With a pecking distance of about 70 thousandths. Feed rate of 10 inches a minute using tool number 1. Now that I've filled in the data, I press save. The block goes into the program, and the cursor advances down. Now that we've told it how to drill, we have to tell the control where to drill the holes. In the case of this blueprint, we have a 8-hole bolt pattern, equally spaced, on a 2.5-inch diameter. We have a cycle especially for that. It's called the bolt hole pattern. We'll select bolt hole pattern from the drill menu, and again we fill in the blanks and answer the questions. The X center point of the hole pattern is 1.75 according to the blueprint. The Y center point is a negative 1.75. The number of holes will be 8. The diameter of the bolt circle itself is 2.5. And the starting angle we can leave at 0. The first hole will be drilled at 0 degrees, and then the rest of the holes will be equally spaced around the pattern. There's no need to fill in the end angle, index angle, or tool number. We've already activated the tool number, so we'll press save. At this point, we have to think ahead and know that the control will have drilled all the holes at this point. Since there are no other holes on the part, I need to turn the drill cycle off. So we go into the drill menu, then select drilling off, and the process of drilling the holes is finished. The next step will be to cancel the tool offset and raise Z up to home position. So I'm going to press mill, select rapid, fill in Z0 and tool 0. That's the Z home position. We save that. The next logical step would be to move off to the side of the workpiece so we can change the next tool. In that case, I'll just hit a modal move, which all I have to do to select that is to press X, Y, or Z. I'll press X -1, Y +1, and save that block. At that point, my tool will go off to the edge of the workpiece to make it easy for me to change. So we're ready to pick up the next tool now and begin our milling processes. We have a circular pocket to mill out, and we have a contour to mill around the outside of the workpiece. We'll go ahead and mill the circular pocket first. So in order to do that, I back up one screen by hitting the previous, and I see the pocket soft key. I'll select pocketing, select circular, and fill in the required data here. Again, the center point for X of the circular pocket is 1.75, the same as the center point of that the bolt pattern was. The Y center point is -1.75. Starting height, 100 thousandths above. Diameter of the pocket is 1.5 inches. The depth of the pocket is -125. Direction, if counterclockwise, is fine. That means we'll climb mill it. A tool step over. You have to think here a second. I'm using a .437 mil. I would think an aluminum .3 is sufficient there. The depth of cut, I'll leave that blank since we can take all the stock in one pass, with the exception of 15 thousandths of finished stock. We can rough mill it at 15 inches a minute. We can finish mill it at 12 inches a minute. And on this entry, we'll also fill in tool number 2 to activate that. We can press the save key. The block is input into the program. Okay, at this point, the pocket will be completely milled, and the tool will finish up directly above the center of the pocket. And the next step will be to make a rapid move off toward the upper left corner. Since I'd like to climb mill around the outside of the part, climb milling around the outside will entail using cutter comp left, as opposed to if I was to conventional mill around the outside of the part, that would be cutter comp right. Since you always view the tool compensation left or right in the direction that the cutter is traveling. So if I look along the first edge of my workpiece here, moving from left to right, if I was to stand behind the cutter and look at it in the direction it's going, my tool needs to be on the left of the path. So that's what we'll use. So I'll select the mill menu, F5, and then I'll select rapid, F2, and I'll rapid off to the edge of the workpiece, X -0.5, and Y0, which will be right on the Y0 line. The reason I'm off -0.5 is so I can put the tool down while it's out in midair and not plunge into any material. I also want to activate tool compensation left at this point in time. We've already activated our tool number, so that's not necessary. And save that block. The next step will be to feed Z down to a cutting depth. So I'll select line, and I'll select Z -0.06 with a feed rate of 20 inches a minute. Since I'm out in midair, that's slow enough. Save that block. The next step will be to program our first line along the top edge of the part here. Seeing that I have a corner radius on the upper right and lower right corners, I'm going to use the corner rounding function. There's no sense in me programming an arc there when the control has automatic corner rounding to it. So I'll select the line, and I'll program the full X dimension, which according to the print is 4.75, but I'll put a corner radius on of 0.4375. I'll also slow the feed rate down here to about 14 inches a minute. Save that block. The next move, we need to move the y-axis in a linear fashion, so we'll select line. The x doesn't change, so I don't need to fill it in. The y, we move to negative 3.5, and again we put a corner radius of 0.4375. Save that. And the next move is also a line, but looking at the blueprint, I don't know the x dimension. I know the y dimension. The y is given as a, well, the y will remain at negative 3.5 for this next move. But there's an angle given with a 35-degree angle and a 0.75 dimension in the y-axis. What I don't know is the x-axis point that I need to feed to right now. So I'm going to go ahead and select a line, and I'm going to use the calculator. First we'll get set up to input the line, and we're set up to input the x value, the unknown x value at this point. Now we'll go to the calculator, and we'll select the center calculator, which is a right triangle calculator. That's what we have here, is a right triangle. So I'll select that, and the calculator comes on the screen, and I have to kind of imagine that this right triangle is based like this one here. In fact, I know that side A of my triangle is 0.75 inches, so I'm going to key in 0.75 inches in side A. I know that angle D is 35 degrees in this case, so I come down and I fill in 35 in angle D. I press Find, and the triangle is calculated and displayed on the screen here. All the sides and angles are filled in. Side B is actually what I need. Side B happens to be 1.0711 inches. That's where I need to move my x-axis to at this point. So what I'll do is I'll put my cursor on side B and press Store, F9. Now when I press Exit, that number is automatically filled into the X display here. And that's perfect. That's just what I wanted. So we'll go ahead and save that and have a line to that dimension. Now we make another line, and this time the X has to move to 0. We're going to feed along the angle this time. X to 0 and Y to a negative, let's say 3.5 inches minus 750 would be negative 2.75. Save. Now I'm going to make another line in the y-axis moving right off the workpiece. Select a line, fill in the y of a positive 0.5, and save that block. Now also when you use tool compensation, you must turn it off after the last move of the contour. I just made a move milling the left edge of the part and moved off the workpiece. Now I have to cancel tool compensation, and you have to do that through a line. So when I select line, what I'll do is move X away from the workpiece, back to where I started, X negative 0.5, but I'll toggle the tool comp to be off and save it. So I've fulfilled all the needs of cutter comp, turning it on in a correct manner and turning it off in a correct manner. Now, the next logical step in the program would be to cancel the tool and raise it up to home position. So I'll select Rapid, Z0, and Tool 0. And then I'll make my modal move, which is just simply an X or Y move with no rapid or line designation. It will be rapid since the last move we input is rapid. I could key in X negative 1 and Y 1 and enter that. Since the move before that was rapid, this move will be rapid until, and all other moves will be rapid until I either program a line or an arc. And we're done with the program at this point. So the next step will be to come up and maybe take a quick review of the program, block by block. You can see in block 1 we set absolute dimensions, we set a peck drilling cycle, with tool 1. We drilled a bolt hole circle. We turned off the drill. We canceled the tool and rapided Z up to home. Moved off to a tool change position. Next, we call a circular pocket with tool 2. And then we wrap it off the corner of the workpiece with tool comp. Bring Z down and make our lines around the outside of the workpiece. And finally cancel our tool compensation, cancel our tool, and move off the workpiece. Looks okay for now. The best way to tell will be to go directly into Draw Graphics. From the main edit menu, F2 is Draw Graphics. When I press that, the draw screen comes up, and I'll just press the Run key. Okay. Now I'll turn the tool display on so we can see the tool drilling the bolt hole circle now. This is an isometric view, so it's a view from our perspective here on the right side of the machine. Okay, I can see now that tool 2 is active and it's coming in to do the circular pocket now. And I can see the numbers change. This is called simulation graphics. I can turn the tool on or off. If I turn the tool off, the program does go faster. The screen simply, it doesn't have to regenerate that tool display, so therefore it's faster. Anytime you drill holes with the tool active, you will get the cylinders along the screen to show you the hole locations. Okay, now we're going along. I could also go to single step by hitting the motion key here, and the tool will stop at the end of each block it's on, and I can just hit the start key. Check my numbers if I desire to. Okay, looks good. And the program is finished. However, our graphics is set up to do the program twice, once with tool compensation and once without. The first time it drew the outside of the part here, it did it without tool compensation. That's the first step. Now it's going to redraw the entire workpiece except using tool compensation on the outside. You'll see when we get to that step that you'll see two different paths. This path is actually the programmed path. The path you're going to see here in a second is actually the path that the CNC takes, which is a compensated position. I'm going to put it in a single step by motion here as soon as this pocket is done. And we can see by the numbers displayed to us on the screen that tool compensation will be active here in a second. Okay. Okay, I just went to single step by motion. And we can see as we move around the workpiece here, my X programmed dimension was 4.75. So if you take half the cutter and add it to that, the number comes out to 4.9687. Half of the tool is about 0.2185. And we can see that as we move around the part. Yeah, you can see we programmed it to X0, but in fact it's at X negative 2187. That's to compensate for the tool. That's what tool compensation does for us. Had we not used tool compensation on this corner down here, I would have a complex calculation to figure out where to actually drive my cutter to. So it looked good in the isometric view. We could always take a quick look at it without text or tool in the XY view. I like to look at it in both those views. Possibly even a front view or an end view if you wanted to see some depths on the part. Okay, there it drew itself without tool comp. And now it's going to do it with tool comp. You can see here in the status area that we have tool 2 active. It's now doing a spiral, then an arc, then a spiral, and then it rapid and fed itself around the part. Okay, that looks all right. Okay, we're going to press exit to turn the draw mode off, exit once again to back us out to the main program directory screen here. We need to press load to load our EX-2 program in as the work program. And when we press exit, we'll be all the way back out to the manual mode. The next step will be to find XY0 or absolute zero on the workpiece using an edge finder, and then do our tool length offsets. Then after that only will we be ready to cut. Now that we've finished programming the workpiece and checking it in draw graphics, we're going to move on to the two setup steps involved in setting up this workpiece. First of all, we have to set absolute zero, in other words, x0, y0, where all our dimensions were taken from on the blueprint. We decided we were going to set that up here in the upper left corner of the workpiece that we're holding in the vise. The second setup steps will involve doing the tool length offsets. So first of all, I'll take my 200 thousandths diameter edge finder and get it up into the spindle here. Set at the proper height, and we'll just hand tighten that. And I need to ensure that my servos are on by resetting my emergency stop, pressing servo reset. Should turn on power to the servo motors here. I'll ensure that my jog mode is in rapid, and I'll press X minus, then Y minus, then I'll set my jog mode to feed and press Z minus. And I'll move close to the workpiece by jogging in feed mode, overriding it down low, until I get near the workpiece. I'll switch it now to jog 100, which is 10 thousandths at a time, and get to my depth and get near the edge of the workpiece. Now I'll go ahead and turn my spindle on. I have the M function hookup on this system. When I hit spindle forward, the spindle turns on and forward in the forward direction. Now what we have to do is jog carefully up to the edge of the workpiece. I'm still in jog 100. I'm going to change it down to jog 10, which is 1 thousandths at a time, and move in one step at a time until the edge finder kicks out of concentricity. Okay, there it is. I'll go ahead and turn off my spindle now. At this point, I know that the center line of my spindle is 100 thousandths to the left of the edge of the workpiece. Therefore, my current position is X negative 0.1. That's what I need to set here in the X display. To do that, I simply press X negative 0.1 and press the Enter key. The Enter key is what sets 0 or any other number in this display here. So when I press Enter, you see the display change to X minus 0.1. Now I will toggle my jog status back to feed and move away from the part in X, and I'll come around to the solid jaw of the vise here. I have to raise Z up a little bit and move down here. We'll slow down the feed rate a little bit and bring Z down. I'm just going to find the positive edge of the workpiece here for Y-axis. Again, I'll get close and I'll turn the spindle on, forward. Go to 10 thousandths jog at a time, and I move in. I moved a little too close, so I'm going to back off and switch to 1 thousandths at a time. And there the edge finder just kicked out. spindle off. At this point, I know that I am sitting 0.100 inches positive to the positive side of Y0. So I touch Y.1, enter, and the display changes. Now we've set both X and Y. I'm going to do a visual inspection by raising Z up. I'll switch my jog back to rapid and press X0, Y0, and hit the start key. As opposed to the enter key, when I press start, the machine will take off to this commanded position in rapid fashion. Okay, so it rapided back to X0, Y0, and I can kind of do a visual check to see that I didn't make a mistake with a positive or negative there. Now that we have X0, Y0, in other words, absolute zero set, that's where all the dimensions of our absolute programming will come from. Now I'm going to give it a command, Z0, and press start. I notice that my Z-axis is -3 inches and some thousandths there. When I press start, it'll raise back up to absolute zero on Z-axis. One important note, before we do tool offsets, which is the next step, please note that setting your XY absolute 0 point with the edge finder and the tool length offsets may be done using DRO mode. In other words, not using the servo power, but using the hand cranks. By using the hand cranks, we're not under servo power and we can crank the machine around and use it just like a digital readout. Before we do tool offsets, which is the next step, I'm going to go ahead and take the edge finder out of the spindle. Now that we've got X0, Y0 set, we have no use for this tool. So I take my tool 1 and tool 2. Tool 1 is a 1/4 inch drill. Tool 2 is a 7/16 end mill in this case. These are not quick change holders, but to get the point across, we're going to use these. So I take my 1/4 inch drill, get the collet up in the spindle, and set the drill in the collet, proper height, and tighten up the drawbar here. Okay, this is tool number 1 in the program. The next step in the process of tool offsets is probably the most important step. Before any tool offsets are done, we have to ensure that there is no previous tool offset active from another program. Say you're running another program and you stopped in the middle of it, and perhaps there was a tool offset active. It could still be active here. What we need to do is look at the status block here after tool and ensure that it says tool 0. If it was to say tool 1 or tool 5 or any other tool, we must cancel that offset before we do any additional tool offsets. So to ensure that, all you need to do is look, and if it says tool 0, you know there's no tool active. In order to set Z home at the proper place, it should be set near the top of the travel of the Z-axis unit here. As you can see, my Z-axis is retracted nearly all the way until it almost hits the limit switch. That's an ideal place to set Z home. Z home is otherwise known as tool 0, Z0. That means there's no tool active and Z is at 0, which it is in this case. Had there been a tool active here, we can quickly get rid of it by going in and making a small MDI program. You could press MDI, come down and press soft key 6, which is tool number, input at tool 0, and then exit out from the program. The message says press start to continue or manual to cancel. So I press start, and if there was a tool offset active, it'll now be canceled. We have tool 0, and we are setting at Z0, and I'm comfortable with the height of the quill here. It's nearly all the way up to the limit switch. If it was not, let's say that it was down that far, we could set a new Z home position. Again, and most importantly, first of all, we note that tool 0 is active. Now we can set our home position. I can jog the quill up carefully until I'm up near the top of the travel. And I can see by the pointer here that I'm nearly there. Okay, now we need to set this position to Z home position, or tool 0, Z0. Tool 0 is active. We're not at Z0. I want to make this position Z0, so I simply press Z0, enter, enter. It's very important, not start. Start would have driven it to Z0. Enter sets a new Z0. So now our Z home position is set, and we double check tool 0, Z0, we're near the top of our travel. So now we're ready to do tool offset number 1. Tool number 1 is in the spindle. I'll set my jog status to rapid and rapid over the top of the workpiece. I'll override my feed and I'll rapid down slowly near the center of the part. And I'll switch to feed jog, bring it down all the way to 10%, and slowly creep Z-axis down till I'm close. Okay, one method of doing tool offsets is to use a piece of paper, set it between the tip of the tool and the top of the work, and jog Z down carefully. I'm going to go 10 thousandths at a time. I can see I still have quite a bit of room. And I'll go down to 1,000th at a time, and I'll jog Z down, moving the paper here back and forth until the paper stops. Paper stops, obviously the tool is touching it. The paper only being a couple of thousandths thick is plenty accurate enough for drilling a through hole. So we're down at the top of the workpiece, and this number in the Z-axis is actually the tool length offset for tool number 1. That's the distance between the top of the workpiece and when Z is at home position. So that distance, whatever it might be, is what a tool length offset actually is. Notice the number in the Z display now. That is actually the tool length offset for tool number 1. The quick and easy way to get that into your tool page where it needs to go is to press F9 tool. Make sure our cursor is somewhere on the line of tool number 1 here. Then we just touch F9, calibrate Z, and this column right here will be filled in. When I press calibrate Z, that negative 3.298 is filled in automatically. The cursor advances to tool 2, and we exit out of the tool page. I'll ensure that my jog status is rapid, and I'll press Z0, start. Not enter, but Z0 start will bring the tool up to 0. And I'll put the feed rate override back up. And the length offset for tool number 1 is now complete. So I'll remove tool 1 from the spindle. And we'll take tool number 2 and get it up into the spindle. First I have to jog away from the workpiece so I can get it in the spindle. And we'll tighten it in. This tool being an actual end mill holder, I can repeat the Z position with it. Normally in a retrofit like this, you'd have a quick change spindle where the tooling will go back into the same position every time after every tool change, therefore maintaining the correct offset all the time. So we'll jog back over the workpiece, switch to feed and jog Z down carefully. I'll go to jog 100, which is 10 thousandths at a time, and I'll bring it down even closer. And another method of doing tool length offsets, especially with an end mill, where you need to be a little more accurate than with a drill, maybe for slot depths or something like that. You can take some blue dye, fan it out on the part here and let it dry, and move your tool over the blue dye and turn the spindle on, and then jog down 1,000th or 1/10th at a time until you see the blue dye disappear. So I'll turn my spindle on forward. I'll go into jog 10, which is 1,000th at a time, and I'll move it down till I see the aluminum be touched by the end mill. Okay, I made contact. Turn off my spindle, and there's my tool length offset for tool number 2. Go into the tool page. I'm on tool 2, so I press calibrate Z. Offset is finished. Before I exit the tool page, I want to check my tool diameters. Tool number 1 has a diameter of 0.25, so I move the cursor to the diameter column, punch up 250, press enter. Tool number 2 is a 7/16 end mill, which is 0.4375. Enter that, and we press exit to leave the tool page. So our tooling information is now completed. One last step, I'm going to raise this tool back up to the home position by ensuring that my jog status is rapid and pressing Z0 start. Okay, that completes our setup of doing absolute 0 for X0, Y0 here on the corner of the part, and for doing our tool length offsets, which remember is the distance from the bottom of the tool to the top of the workpiece with any particular tool that you're using. The control holds up to 99 tool offsets, so there's plenty available.
The Series 1100 has 3 calculators which, when used properly, can save hours of programming time at the machine. Here's how it's done. All 3 calculators can be accessed from the edit mode by simply pressing the F7 key. The first calculator is a math and trig calculator for adding, subtracting, multiplying, dividing, performing trig calculations, etc. The second calculator is a right triangle calculator for figuring out sides and angles of triangles. The third one is a geometry calculator for inputting points, lines, and circles, and for finding tough-to-define tangency points and intersections, much like a built-in CAD/CAM system. All 3 calculators have store and recall functions, so that any XY coordinate found can be inserted directly into the CNC program that is being worked on. Not only is programming time and effort saved, but many potential keystroke errors are completely eliminated. We'll start with the math and trig calculator. When we select it, it comes up on the screen and the soft keys change to plus, minus, multiply, divide, left parentheses, right parentheses, function, including sine, cosine, tangent, etc., clear key, store key, and an exit key. For example, we could key in 3.125 divided by 6 to find the increments between 7 holes. And when we press enter, we get the answer on the bottom. We can then store that answer and insert it anywhere in the program now or later on. Clear that, and we can find the sine or cosine of a certain angle. For example, enter 35 degrees, function, and select cosine. The cosine of 35 is displayed at the bottom. Once again, I can store that answer for later use. The second calculator is the right triangle calculator. When we select it, it comes up with a window in the center of the screen, and the default triangle is shown in the upper left-hand portion of the screen. It labels side A, side B, side C, angle D, and angle E. Simply key in 2 pieces of information, and the calculator will do the rest. Let's say that side A was 1/4 inch long, and we knew that angle D was 25 degrees. We key in our 2 pieces of information and press Find. The resulting triangle is drawn on the screen to actual scale, and all of the missing values are filled in for you by the control. So now we know that side B is 0.5361 inches long, side C is 0.5916 inches long, and angle E is 65 degrees. We can pick and choose any of those values to store in a separate little piece of memory to be inserted into the program later on. The last calculator is our geometry calculator. The geometry calculator is used for inputting points, lines, and circles, similar to a CAD/CAM system. The left-hand column of icons is used for inputting points onto the screen. The center column is used for inputting lines. The column on the right is for inputting circles, with the exception of the last two definitions, which are used to input lines tangent to circles. I'll give you an example of an oblong slot. We know the center point and radius of the first circle, so we can choose the center and radius icon. It prompts us for a radius value, so we enter 1.25. We then define the center of the circle, x0, y0. The circle appears on the screen. I'll repeat the process for the second circle. I select the center and radius icon again, and I'll enter a radius of 0.75 this time. The x-center is 5 inches, and the y-center is 0. There's the second circle. Now let's say we want to put lines tangent to these two circles. I'll use the line tangent to two circles icon. Select it, and it asks the number of the circles to draw the line tangent to. The first circle is 1, and the second circle is 2. It shows us two tangent possibilities and gives us the option of choosing either one. Each one is numbered, so I'll choose number 1. Now, I want to put a line tangent on the bottom. I'll choose the same icon we used before. This time, the line is tangent from circle 2 to circle 1. I select option 1, and the correct line is drawn for me. Now, the ultimate goal is to find out exactly where the lines intersect the circles. So we go to the point definition, showing the intersection of two elements. When I select it, it asks me for the element numbers. The circle is element 1, and the line is element 3. I select those elements, and the point is input automatically. I repeat the process for the remaining tangency points until all of the intersections are found. Conventional CNC programming usually requires many point definitions, whether it's the center of a circle, the intersection of two lines, the intersection of a line and a circle, etc. Therefore, the geometry calculator can save a lot of programming time while eliminating the need for expensive offline programming systems. The recall function allows us to insert XY coordinates from the calculator directly into our CNC program. For example, when programming the first arc in the programming example shown above, simply select Recall, then select the geometry calculator. All the geometry that I saved comes up on the screen. If I select point number 5 and select X and Y, both its X and Y coordinates will be automatically input into the arc statement. If I want to do a line to the next intersection, I would repeat the process. This time I would select Line, Recall from the geometry calculator, select point number 6, and choose X and Y. The XY coordinates of point 6 are input directly into the CNC program. I can continue to recall from the geometry calculator at any time and input all necessary XY coordinates until my part program is completed. Values can be recalled from any one of the three calculators. If I were doing a drilling operation and I wanted to recall from the first calculator, I could select one of the stored values and input it onto the screen. The same is true of the right triangle calculator. If I were getting ready to machine an angular move, I could recall any saved value. In this case, I could select either angle E or side C from the stored values and input them directly into the control. I could then save the block in the program or execute the block as an MDI move. Not only can the calculators be used to find mathematical values or perform simple CAD/CAM functions, but the results can be inserted directly into the program without having to memorize them or write them down. This completes the Series 1100 training program. Stop the tape here and make sure that you can do all of the programming examples on your own. Remember, the more that you practice using the system, the easier it will become. Good luck.